welcome back to Physical Science. This is Mr. B. We're going to continue on with phase changes, and again, we might have a guest speaker for this video. Mrs. B might help us out a little bit on this one. So, again, now we're actually going to get into the specifics of the actual phase changes. Again, we talked about just how the energy is transferred, either absorbed or released, and so now we're going to get into the specifics of what they actually are. So for our first ones, probably the two most common ones are melting and freezing. So a couple questions, or actually one question, we're going to ask ourselves is how does the arrangement of water molecules change during melting and freezing? And so the answer to that one is the arrangement of molecules in water becomes less orderly as water melts and more orderly as water freezes, which makes sense. Again, this is exactly what we talked about when we first introduced solids, liquids, and gases. So obviously as water freezes, it's going to be into the solid stage, and when it's melting, that's when it's in the liquid stage. So melting is our first one. So each water molecule contains 2 hydrogen atoms and 1 oxygen atom, which is H2O. So in ice, attractions between water molecules keep the molecules in fixed positions. And again, that's, remember, talking about how in solids they kind of vibrate around one position. Again, they don't change places with their neighbors. That's what it's going to happen in water as well. So any energy gained by the water after a phase change will increase the average kinetic energy of the molecules, and then the temperature will rise. And as that temperature will rise, that is when we're going to approach melting. So when ice cubes are removed from the freezer, heat flows from the air to the ice. So again, that is how it's going to move. Heat's going to kind of go from where there's not a lot, or it's going to start where there's a lot, and it's going to move to where there's not a lot. So as the ice gains energy, the molecules vibrate more quickly, again, which is what we just said. And at the melting point of water, which is 0 degrees Celsius, some molecules will gain enough energy to overcome the attractions and they'll move from their fixed positions. So this is when the melting process really begins. And again, remember we said though during a phase change, it's not going to change temperature. It'll stay at that 0 degrees Celsius until all of the molecules have overcome the attractions.
Is that an endothermic or an exothermic?
What do you think? Because I think it is actually an endothermic because the energy is being absorbed, and if you referred back to our last one, it actually says melting is an example of an endothermic change. But good question over there. And so again, once again all of the energy has been absorbed, when all the molecules have enough energy to move, melting is complete, and after melting is complete, the temperature will continue to rise. So that is melting. Where are we at here? Okay, so now freezing. So our next one is often people think of cold temperatures when they heard the term freezing, but substances that are solid at room temperature can freeze at temperatures that are quite high. So for example, silicone will freeze at 1412 degrees Celsius. So again, all freezing means is changing from a liquid to a solid, so it doesn't necessarily mean it has to be done at a cold temperature. It is, because as you can see right here, that is quite high temperature right there for silicone. And any energy removed after the freezing is complete decreases the average kinetic energy of the molecules, and then therefore the temperature will drop.
Therefore it's an exothermic?
Very good, because energy is released.
Or exits.
Or exits, yes, that might be a good way. Energy exits in an exothermic change. Okay. And so now we're going to get back to our example that might make freezing a little bit more sense, is when we talk about liquid water. So when it was placed in a freezer, energy flows from the water, because again, when you put the water in, it has more heat than in the freezer, so it goes from the water to the air, and then the water will cool. So again, just the heat leaving the water. So as the average kinetic energy of its molecules decreases, they move more slowly. So at the freezing point of water, some molecules move slowly enough for the attractions between the molecules to have an effect. So this is when they come back to having the more orderly arrangement that you find in solids. And when all the molecules have been drawn into an orderly arrangement, freezing is complete. So literally, freezing and melting are exact opposites of one another. Again, melting, they become less orderly. They overcome the attractions. Freezing is kind of making the attractions more prevalent, making it a solid, and making it in a more orderly arrangement. So melting and freezing kind of go hand in hand with one another, and again, those are probably the two that you're the most familiar with. So our next two that kind of go hand in hand with one another are called vaporization and condensation. So the phase change in which a substance changes from a liquid to a gas is known as vaporization. And again, so vaporization is an endothermic process. So what does that mean? It does what to the energy? It absorbs the energy. So 1 gram of water gains 226 are 2,261 joules of energy when it vaporizes. So this amount of heat is the heat of vaporization for water, and it varies again from substance to substance. So again, water, it takes 2,261 joules again to overcome those attractions and turn it from a liquid into a gas. And again, each substance is going to have a different temperature, a different amount of energy required for that heat of vaporization.
So you could say it's a joule thief.
You could say that, I guess. Okay, where are we at here? So in a refrigerator, phase changes actually help keep the food cold. So this is going to be, again, a real-life example of why we need to know about vaporization and condensation. So it says energy from inside the food compartment is used to change a liquid to a gas in the evaporator. So inside of a refrigerator, again, we're going to see a picture of this here in a second. Energy is released when the compressed gas changes back to a liquid in the condenser, and during these phase changes, energy flows from the inside of the refrigerator to the outside. So again, here's kind of how the process works. Again, the energy is removed from the food compartment and it comes to the evaporator, and it goes down into the condenser, and then the energy is released to its surroundings. So again, keeps the inside cool and kind of pushes the heat to the outside. And then we'll explain that one a little bit more in class, because again, that's a little bit harder to understand again for the first time. So we'll go over that one more a little bit later. So again, now we're going back to the evaporation, which again was kind of mentioned in the refrigerator example. So after a rain shower on a sunny day, or sunny warm day, you may notice puddles of water after a few hours. The puddles may be gone due to evaporation. So evaporation changes the substance from a liquid to a gas at temperatures below the substance's boiling point. So here's the big difference between evaporation and vaporization. Again, they sound similar, and again, they kind of are similar, but evaporation changes the substance from a liquid to a gas below the substance's boiling point. So again, we usually think of going from a liquid to a gas by boiling, but this does it below there. So we're going to take a look at how that works. So evaporation takes place at the surface of a liquid and occurs at temperatures below the boiling point, which is what we just said. So we'll get a real life example here. So the water level in the bird bath decreases over time. So some molecules near the surface are moving fast enough to escape the liquid and become water vapor. So the greater the surface area of the container, the faster the water evaporates. So you might have noticed this. Again, the more deep, maybe, or the more like kind of depth there is to water, the less it's going to evaporate. But if you take that water and you spread it out over a thin surface, again, that means that there's a greater surface area. That means it's going to evaporate more quickly because, again, the water molecules at the top can kind of get a little bit heated, they get sped up, and they're kind of able to overcome the attractions that usually hold them in place without boiling point actually coming up. So that is how evaporation works. So again, evaporation is a form of vaporization, but it's a little bit different. And when water evaporates in a closed container, water vapor collects above the liquid. So if we had, again, maybe in a closed container we had some water and put it to some higher temperatures, we could notice this. So the pressure caused by the collisions of this water vapor and the walls of the container is called vapor pressure. And the vapor pressure of water will increase as the temperature increases, and at higher temperatures, more water molecules have enough kinetic energy to overcome the attractions of other molecules in the liquid. And again, we'll talk about this a little bit more in class. So that's it for this video. Let me know if you have any questions.